We start the recording and then we'll continue. Okay, so yeah, so any questions from the last lecture where we were more or less discussing the deflection of charged particles in electromagnetic fields? And well, that deflection includes the forces that would be acting on these particles. Any questions from that?
No, sir, no questions.
Okay, so if there are no questions, okay, so let's continue this new topic that we started, which was how do we experimentally in lab measure this charge to mass ratio? And then we'll also look at some of the problems that are concerned with the deflection of a charged particle, right? So let's continue from over here, the charge to mass ratio. So I was telling you that you have this spherical container, tube-like. It's a sphere, a ball-shaped object, and in that you have a source that is capable of throwing out, spitting a beam of electrons. Now, this tube is placed in between two coils. These two coils, one coil is in front of this sphere, and the other coil is at the back of this sphere. And then you run you apply some potential difference across the two coils, and so the current runs through these two coils, right? Now, what would that do? That would basically, because charges are moving, what is current? Motion of charges. That would create a magnetic field in this region. And because of that magnetic field, you would obviously expect then, as we have discussed, that the path of this beam of electrons will be deflected. Now, this field can be controlled by the amount of potential difference that I am applying. The potential difference is essentially accelerating these electrons, right? So if I increase the potential difference, the acceleration will also increase, which means that the charges will be moving at a much faster rate. And so we know that FB is BQv. So if velocity of these charges is very fast, that would imply a stronger magnetic force, which would imply a stronger magnetic field. So a stronger magnetic field would be generated, right? So,
Sir,
yeah.
Sir, B is the magnetic field?
B is the magnetic field, yes. So I think everywhere that we have been discussing, we did not use B for any other variable, right? It's always been a magnetic field, or at least in electricity and magnetism, B is always the magnetic field, right? And then this is just the extension. Charged particles, just the extension of electricity and magnetism. All of these just really comes in under the subject of electrodynamics, really. Right? Anyways, so where was I? Yeah, so that means that we can control this potential difference that I'm applying through these coils, right? It's a voltage generator or something, you can say. There's a knob on it which you can rotate and change how much potential difference am I applying. So according to that potential difference, you can see how does the magnetic field change, right? And when you can see how does the magnetic field change, you can see how does the magnetic field change by using an equation, and then you can visually see, practically you can see the deflection of an electron, at what angle it is being deflected, or the diameter of the circle that it's forming, right? And then you can relate, diameter, and then that is just the radius, right? 2 times the radius, so essentially it is just the radius. And so you can then relate radius and these potential difference, right? Radius and the potential difference that you're applying across the coils. Okay, so is that clear? Okay, so let's see. Okay, so essentially what we are doing is we have set up this entire experiment. We are applying some potential difference, and the result of all of whatever happens in between, the result of all of that is the deflection of the beam of electrons. So we want to relate this potential difference to this deflection, and then we can from there find out the charge to mass ratio in the lab, right? So let's see. Now what happens is when this charged particle, a moving charged particle enters a magnetic field, what happens is it experiences a magnetic force, right? And this is what we have been discussing upward in this part where we discussed deflection. I told you that measuring velocity of these particle electrons is not a very practical thing to do. So but we know we can measure the voltage. We are applying that voltage. We can control it. It's in our hand. So we'll write it in terms of that potential difference. So we'll start our doing that from considering energies, right?
Sir,
Conservation of energy. Yeah.
sir, V is velocity or the volt?
Oh, this small v is velocity, right? Usually I write velocity with this little, curve at the top. That usually represents velocity. Potential difference I always write with capital V, right? So I'll write that down in a bit now, and you'll see. Okay, so we'll recall our conservation of energy principle. And according to the conservation of energy, what is happening is electric field. When I have electrons in there, there is some electric field, and that electric field is doing some work to provide the kinetic energy to these electrons, right? Magnetic field is not doing the work. Magnetic field only bent the path of electrons. Electrons were already moving, and so when electrons were already moving, how were they moving? Because of the work done by the electric field that they had, right? So and essentially in the universe there is no such thing as a stationary electron, by the way. So electrons are always moving here and there. So the conservation of energy states that the work done by electric field is equal to the gain in kinetic energy. I write it as Ek of the electrons, right? Okay, so mathematically, I can say that the work done is the change in the kinetic energy. Now, what do we know about work done by an electric field? The work done by an electric field is the charge times the electric potential, right? Every time work done is written as a quantity times a potential. For example, in gravity, the source of gravity is a mass, right? So mass times gravitational potential is the work done by gravity. In charges, the source of the electricity or electric fields or electric force is a charge times a potential. In this case, electric potential will give you work done by electricity or electric field, right? So the work done is simply Q times capital V. So this V is capital. This V is the potential, right? So I'll just write it over here. potential. And this is equal to the kinetic change in kinetic energy of the electrons. So of course, the electrons are emitted from this, right? They're accelerating, so their its speed is continuously changing. So it is half m delta v squared, which is just half m v squared minus u squared. Right. Now, let's suppose that initially, when there was no electron, right? Initially, the beam was turned off. The speed of the electrons, because again, this is a kind of a vague statement to say speed of the electrons was 0. There were no electrons really at that point. So the initial speed then is 0. So suppose if u is 0, that initially there were no electrons. So you can say that the particle was initially at rest, or the electrons were initially at rest, but then again, it's not a right statement. So I'll just stick with this, and this gives you q times v is half m, and then v squared, right? So this is what you're left with. And now what we were looking for since the beginning was a charge to mass ratio, right? But whatever I'm doing right now is to determine velocity in terms of potential difference, so that I can go back here and replace that, right? In the charge to mass ratio, where did I write that? Q over F, this one. So I want to replace the velocity with a potential difference type of term. So in this, whatever I'm doing downstairs, I want velocity on one side and all other quantities on the opposite side. So doing that, just rearranging this equation, it's not a big deal. This is velocity. So velocity is equal to square root of, so 2 goes there, 2q capital V, and then m goes in the denominator, so that's divided by m. Right? And to get rid of the square, we just square root the entire thing. Again, this V here is the accelerating potential difference, or the accelerating voltage. Now, this is the parameter that I can control in my experiment. So what I'm going to do is I'm going to take this expression, and let me label this equation as equation star, and I'll say that I'll put this put in equation star. So you see, equation star was q. Actually, let's do it on the other page, right? So let's borrow this expression for velocity over here. And where's the next page? Here we go. And let's put it over here. So this is the expression for velocity, the expression for charge to mass ratio. What was that? Let's go back up here. V over RB, right? So velocity over R times B. So now let's replace this velocity with this expression. So this gives me charge to mass is equal to square root of 2q V over m divided by RB. But this is not quite right still, right? Why? Because you can see that you still have a charge on both sides of the equation. On the right hand side, it's under a square root. On left hand side, it is just sitting up there, right? So charge is not completely, what do you say? I forgot the word, but it should be, it is not completely factored out, you could say, right? So we want to factor this charge out and bring it completely over here on this side, so that we really have a charge to mass ratio. So we can do that if I square the equation on both sides, right? So let's utilize this space. Square equation, let's call it equation alpha. Equation alpha. So what does that gives you? that gives you q squared over m squared is equal to, the square root gets, you can get rid of the square root. This gives you 2qv over m divided by r squared b squared. Right? So this is what we are left with. Now you can see that this charge cancels with this one, right? This mass m cancels with one of this one, and you're finally left with q over m is equal to square root, sorry, not square root, q over m 2v over r squared b squared. And this is the equation that we were looking for. Now, how do we use this equation, right? So I told you that this equation was really no good, right? This q over m v, small v over rp, because we could not really tell the velocity of those electrons, right? So, but this equation, if you look at this one, let's see all the parameters to the right side. First, we have, well, 2, just a constant. Then you have V, capital V, that is the potential difference. And then again, like I told you, you can control that by using a knob on your voltage generator. Then you have R squared. R is what? It is, remember, it is the radius of the path that the electron follows, a circular path, right? And if you go back over here, I told you that the deflection can be controlled by adjusting the potential difference, and you would see a circular type of arc being formed. Then you can simply measure by using a scale or a ruler. You can place it in front of the sphere, and you can measure this distance, right? And so you can get the radius as well. This is something that you're practically doing. And then the value for B is also obtained, because you have the potential difference, and then B can be obtained from that potential difference. So this is the equation for charge to mass ratio that is useful to us when we're doing performing an experiment. Okay, so is that clear? Any question from this thing?
No, sir, it's clear.
Okay. All right. So, okay. So yeah. Okay, one more thing that we can see is, suppose if I have the same thing, a region of magnetic field inside this circle, right? There is a, so I'll just highlight that by this thing, that there is the magnetic field in this region. What that means is now, if I bring an electron in there, I know that it is going to be deflected, right? But there is something that I can do so that the path does not deflect at all. Can you tell me what is that? What could be? Just take a wild guess. So what I'm doing is I'm taking an electron, a beam of electrons, and I'm throwing it over here. So this is a beam of electrons. Now, if there is a magnetic field, so far you should be able to identify that the path is going to be deflected because of the magnetic force that is acting inside this magnetic field on the particle. there is something I can do in it by changing a bit, by adding at least something to the experiment, by which the path of the electron does not deflect at all and just passes right through it.
Is it by applying another magnetic field in the opposite direction?
Okay, that is really a wild guess. Let's think of something else. Maybe you can apply electric field, right? So of course, if you are applying a magnetic field in the opposite direction, suppose in this case it was in, then you apply out. If you can somehow manage to keep their magnitude same and all of that, because magnetic field is a vector, they would essentially cancel out, and so the path would be straight. So that's correct, right? But in terms of the entire thing, right? Because you know, if I have electric field and magnetic fields kind of coexist, right? So if this is my electric field, you know, these are transverse waves, right? Electromagnetism. Uh, the magnetic field is always perpendicular to this electric field. So if I'm drawing this, this is in this plane, right? While the electric field is in this plane. So you can see that they're at 90 degrees to each other. So if I apply a potential difference across these, suppose that I make this plate positively charged and this plate I make it negatively charged, then there would be some electric field, right? So the electric field would be going from positive to negative, right? However, you remember that this is electron that we're talking about, which carries a negative signature with itself. So the force that it would be experiencing is downwards. So let me just draw this path, which is going to go straight. So it would be experiencing some electric field in this direction, sorry, some electric force in this direction, and there would be a magnetic force in the exactly the opposite direction, right? Because these two fields that are produced are perpendicular to each other. So this would there would be a magnetic field over here. Can you tell me now what can I do to this electron now, at least? So well, now I have these forces. It's the electric field. I've applied the electric field. Can you just suggest what could I do to the kinematics of the electron to make sure that it goes straight without being deflected? If I can find a value for the velocity, right? The velocity that I can give to these electrons, so that the velocity is so fast that well, not really fast. Fast is not the appropriate word, but it's an optimum velocity such that the magnetic force, which is QVB, has a velocity term in it, will be completely balanced by the electric force. So in that case, throughout this entire journey, right, let me try to kind of animate this thing. Oh, well, that didn't work. Okay, so it would be something like this. Throughout the entire journey, the electric field and magnetic force, are constant throughout, right? And they're balanced, exactly balanced by each other. So that's why the path of the electron does not deflect because it is balanced by the electric and magnetic force. Okay, so what does that mean? I want a velocity that can achieve this goal, right? And this is sometimes called velocity selection or velocity selector, right? So again, the condition is that the magnetic force should be balanced by the electric force. Magnetic force is Q V B, while the electric force is just Q times the electric field. What does that gives you? This gives you charges cancels, and it gives you a value for velocity as the ratio of E to B. What does this mean? What does this tell you? This equation tells you that if I use a specific value of this electric field and magnetic field together, then I can achieve a particular speed of this electron such that it does not deflect in this magnetic field, right? So is that clear? The electron is going to pass straight through this, the magnetic field. Okay, so any questions?
No, sir.
Okay. All right. So, okay, now let's do some problems. Let's start with this one. Suppose that you have a proton, right? And the mass of the proton is given to you, which is 1.66 into 10 raised to power minus 27 kilograms, right? And we want to accelerate this proton to reach a speed of 8.0 into 10 raised to power 6 meters per second. So what I want to do is I want to accelerate this proton so that it can achieve this velocity. For that, what potential difference will I need to apply to this proton such that it is accelerated to this value of speed? Okay, so think about this, that we want to give it some speed, right? And what we're doing is we're applying some potential difference. Potential difference corresponds to the electrical potential energy, right? And whatever potential I apply, that is directly correlated with what potential energy I'm giving to the particle. Now, if we ignore all the air resistance and all of that, then all of this potential energy is going to be converted into the kinetic energy of the electron as it starts to move, right? So by conservation of energy, how will we solve this problem? I'll say anyone? Okay, so by using conservation of energy, what do we have? What we are doing is we are applying potential, right? So V and the potential is being applied, and the potential energy is by multiplying what is the source of that electric field or the potential, which is a charge in electric fields. And this is being converted, this will be entirely converted into the kinetic energy of this proton as it moves to this velocity, which is half mv squared. This is curly V, velocity. Now you can easily rearrange this equation as V is equal to mv squared by 2q, right? And now it's just a matter of putting in the values. The mass for the proton, the mass would be the mass of proton times the velocity, which is 8.0 into 10 raised to power 6, divided by 2 times. What is the charge of a proton? I think it's 1.6. It is the elementary charge, right? 1.6 into 10 raised to power minus 19 coulombs. So this gives you a potential difference of 3.3 into 10 raised to power 5 volts. Is that clear?
Yes.
Okay. Let me see how much time. Okay. Let's try to quickly do another problem. Now, suppose that you accelerate a proton through a potential difference of, now the potential difference is given 2.0 megavolts, right? And what we want to do is we want to find the kinetic energy that this proton is going to gain. Again, the mass of the proton will be given to you. The kinetic energy that this particle or proton gains when it's accelerated through this potential difference. It's exactly the same logic that we applied in the previous problem. Potential difference corresponds to potential energy, velocity corresponds to the kinetic energy. So that would just mean that this thing, QV is equal to half mv squared. And then this is the kinetic energy, and that's what they have asked us. So this is just EK. So if I multiply the charge of proton with this potential difference, I can figure out the kinetic energy. Again, it would be 1.6 into 10 raised to power minus 19, which is the charge, times 2.0 into 10 raised to power 6 volts, because it's megavolts. And this would give you the kinetic energy, right? It's 3.2 into 10 raised to power, so this is minus 19 into 6, so minus 13 joules. Is that also clear? A pretty straightforward question.
Yes.
Okay, clear?
Yes, sir.
Okay, so let's finish this with this, finish the class with this, less than 1 minute remaining. In the next class, we'll be starting with the final topic of this chapter, which is the Hall's effect, right? And by tomorrow we'll finish this chapter, and then we'll start with the next one. Okay, so